Thank you. And well, of course, I would like to start by thanking the organizing for putting together this great meeting, which I've been enjoying very much so far. I'll continue on the topic of equilibration of isolated quantum system, a topic that you've heard about in the previous talk. And what I'll be adding as an ingredient now is what I here on this slide call locality. So I'll look at equilibration times, so the relevant timescales on which this happened, and locality. I'll define later on precisely what I mean here, but for now think of it as long range versus short range. So more local interaction will be short range and less local ones will be long range. And a precise definition will come rather late in the talk for a technical reason. This is work in collaboration with Daniel Nicholson, former postdoc in my group and now at the University of Augsburg. So let me start with a very simple sketch, equilibration in isolated quantum system. We want to prepare a quantum system in a non-equilibrium state. Think of having two blocks of matter at different temperatures, putting them together. And the expectation is that after having waited for some time, they will be in an equilibrium state, and it will take a certain time scale until this happens. And we know from experience that in macroscopic settings, very often this is a time scale that we can observe. So it happens neither instantaneously nor at astronomical time scales, at least in condensed matter. And these questions, what is the time scale, what is determining this time scale, this is something I'll be looking into. Before I get to this question of time scales, I will motivate a bit why I would, in this talk, I would combine the equilibration time scales and the question of locality. Why is that an interesting question that interested me enough to work on it for some time? So I'll give two motivations. The first one is the convenient one for this audience that has an interest in long-range interactions. So motivation one, it has been reported early on in the study of long-range interacting quantum systems that there are instances where these long-range systems equilibrate incredibly fast. And this is also the motivation why people say that, and I have also shown that for certain applications in quantum information, for example, you can speed up certain tasks because certain things in these systems happen very fast. And I think it has a rather intuitive explanation. Because of all these many links to all the other states, it can be easier to connect something that happens on this side of the system to something on the other side. At the same time, it was also reported that there is a strong tendency in long-range interacting quantum systems to have long-lived quasi-stationary states. So a situation where equilibration, well, there happens something like pre-thermalization. You go to some state that looks almost equilibrated, but at a much longer time scale, the system only will equilibrate properly. And applications of interest would be that this could be used to construct non-equilibrium quantum matter without driving. So you just say, I remain in a non-equilibrium state for so long that I could use this as an almost equilibrium state, and which may have properties that you cannot have in equilibrium. So the observation here is that there are competing effects at work, something that can make equilibration very slow and another effect that can make it very fast. And these competing effects may make it a bit harder to study this problem on a quantitative level. What I want to do is I want to do a quantitative study of these timescales, and what I would also like to do to understand the general principle and why these timescales occur in equilibration. And so I would like to have results that are not for specific model systems, but for broad classes of systems. And when you ask such a very broad questions, you usually have to be more modest in what kind of result you try to derive. So usually it will be not like an exact statement. but something like a bound or a typicality statement that for typical systems in that class, this and this happens. And this is what I will get into later on in the talk. So that was the motivation one for people already with an interest in long-range interacting systems. I get to motivation two, even though it may not be needed for this audience. I think it's just interesting to hear about where this kind of question popped up in a different context. And you may have heard that in the past 2 decades roughly, there was quite some interest in deriving equilibration from microscopic principles. So it's a topic where you start from the Schrödinger equation and try to show that, prove in some way that equilibration in a suitable sense happens. And buzzwords are, well, the rediscovered paper by John von Neumann from 1929, or the topic of canonical typicality, usually that was started a bit by the Rutgers statistical physics groups and so on. And the flavor of a typical result that was derived in this context, this is now very, very loosely speaking, is you have something like a typical Hamiltonian and a typical observable, and then you would like to, or then you show that for all initial states, you have some quantity. I'm not going to walk you through the symbols here, but this quantity is only non-zero if you have a significant non-equilibrium observation. If you measure your system and you see something that is away from equilibrium, this here can be a non-zero quantity. And the statement is now that this quantity, or integrated over times, is bounded by something that is incredibly small. So usually something like doubly exponentially in the system size small. And the statement is that this non-equilibrium indicator is essentially always zero, except for very rare instances, when you do this integral for sufficiently large t. And this sufficiently large t, this is now the equilibration time. If you look at the system only initially, it may very well be in a non-equilibrium state. But if you wait long enough and average over all this, at some point you will only see equilibrium, except for these very rare instances. And then this statement holds true. So the rigorous mathematical statement says there is a sufficiently large t, but it doesn't specify the t. So a result like this here explains the ubiquity, the fact that we observe equilibration so frequently in nature, but only if the corresponding t dependence is realistic, like not the age of the universe and not instantaneously, but something that we observe in nature typically. So something, I would say, between maybe femtoseconds and millions of years is maybe a reasonable time scale, but not something that is astronomically large, like exponentially in the system size or something like that. So what people then try to do is to use similar techniques like those that were used to obtain this result, so typicality techniques, whatever that is in detail, to show what are the typical timescales on which this equilibration happens. So, and the hope was that would give a reasonable result. And there's a very nice paper there where this technically very demanding work was done, but the result was very disappointing. So the result was that the typical timescale is of the order of the Boltzmann time given here, which is super fast. So these systems typically, if you take a typical system in the sense of randomly you draw a Hamiltonian and you draw an observable, and then these systems will equilibrate super, super fast and do not describe what we observe typically in nature. And the same authors came up with a conjecture what went wrong essentially in their calculation. I mean, there's nothing wrong in the calculation, but why it wasn't the right calculation to do. And the conjecture is that locality of Hamiltonian and observable are crucial ingredients to obtain realistic equilibration times. So I would like to rephrase this in a bit provocative way, saying that physics is not typical, and some people working on random matrix theory often don't like that statement. But anyway, so it would be great to do a similar calculation and include locality in here, but this makes it technically a lot harder. So I will try to do something simpler, not do a typicality result, but include locality in the following. So before I get to the question of how locality influences the equilibration time, I want to give a little bit more technical introduction of what I will consider as equilibration, like what notion of equilibration I'm going to use. And so the setting, well, some Hamiltonian on a finite dimensional but very large Hilbert space with a discrete spectrum, and I can always write this here in terms of the energy eigenvalues and the corresponding projectors. There may be degeneracies or not. It makes it technically more difficult maybe to have some, but I don't want to go into this. And then a very simple statement: since we have unitary dynamics, we cannot have equilibration in the sense that the density operator as a function of time converges to some equilibrium state. This is not going to happen, and the result you can write in many ways, or the reason why this is, if you look at some observable, for example, and the time evolution of the expectation value, you can write it out in some way that consists of time-independent prefactors, so some time-independent prefactors, and then these phase factors in here. It's all only phases rotating, and whatever these energies and these prefactors are, this will always be quasi-periodic behavior. You'll get arbitrarily close to the initial value at some point, so it's going to be quasi-periodic and may look like this. So this is now time. This is the expectation value of the observable minus the equilibrium value. So equilibrium is here at 0. I will start somewhere out of equilibrium, will equilibrate and be at this value with tiny fluctuations for most of the time. At very late times, there may be occasional rare excursions away from equilibrium. So this is all very well known and not so new. I like the statement that this equilibrium state, this rho equilibrium, is not a physical reality, but more a crutch. It's helpful to calculate something, but your system will not be in that state. It's only a useful thing to calculate properties of the state that your system really is in. And then the observation I've mentioned before, equilibration, the system will look equilibrated, not for all, but for most t, and one can give more meaning to that statement. And thirdly, not all observables equilibrate. You can always construct something that keeps on oscillating with large oscillations forever, but doesn't equilibrate. And this motivates to define equilibration with respect to a chosen observable, or with respect to several chosen observables, where you say, these are the quantities I can measure. I consider my system equilibrated if these observables take on their equilibrium value. And it's not that this is something, well, because I cannot measure more, but because if you include all observables, you will always have some that do not equilibrate. So it is also a very reasonable thing to do. So now let's get to the notion of equilibration I would like to use in the following. So I'll just write O for observable. It could be several observables that I combine into this notion. That doesn't make a difference here. There is the notion of strong equilibration, like the expectation value of some observable really converging to an equilibrium value. But as I mentioned before, this would look like this here, really going to equilibrium. We cannot have this in our setting of an isolated quantum system. So not of interest here. Then probabilistic equilibration of expectation values, so that the expectation value as a function of time is very close to the equilibrium value for most of the time. This is a bit more formal statement in terms of a probability, but it's the same. This is the plot I've shown you before with tiny fluctuations and a rare larger excursion about the equilibrium value. This is a useful notion of equilibration, but it has its shortcomings as well. What could that shortcoming be? Well, even if the expectation value here is close to the equilibrium value, if I now do a measurement, it may happen that the actually measured values, which are plotted here as these dots, even though the expectation value is 0, that I measure very large positive or negative measurement values, and still the expectation value is 0. I would say this is not what I would like to have when I call a system equilibrated. My expectation, it's a choice, would be that no, it's equilibrated when I measure the system and really I find the equilibrium value of the observable in the measurement. So this is what I would like to have, and this is what the third definition here covers. So there's different ways to enforce that you find them. You can say, well, the fluctuations here have to be small as well, or a more formal notion, probabilistic subspace equilibration. You define an equilibrium subspace spanned by all those vectors from the Hilbert space that are eigenvectors of the observable with eigenvalues that are very close, like delta O close to the equilibrium value. And the subspace then consists of, if you are in that subspace and you make a measurement, then you will find the equilibrium value of the observable. So this achieves what I said before, what I would like to have. The observable evolves in time. I do a measurement and I find a measurement value that is very close to the equilibrium value. And this, of course, also happens only for most times. There are the rare excursions that I had here. They exist also in this setting. So this is what I will use as a notion of equilibration in the following. And just as a quick reminder, I'm talking about equilibration here, which is a more general notion than thermalization. I'm not going to ask whether the equilibrium state is a thermal state, like a Gibbs state. This is a different question. Interesting, difficult, but not the topic of this talk here. All right, so back to locality and the conjecture of Goldstein, Hara, Tasaki that I mentioned before. Locality should be a crucial ingredient to obtain realistic typical equilibration times. And so the question, what is special about the Hamiltonian and the observer being typical? Being local. What is a consequence of the fact that these are local? Well, one statement is there exists a basis in which both are simultaneously sparse. Well, just use the site basis. I mean, if these are local interactions, then they will be sparse matrices. And there is a related result by these people here that say if a local Hamiltonian, if you take a local Hamiltonian and a local observable O, and you express the Hamiltonian in the eigenbasis of the observable, it is almost banded. Almost banded meaning you have a banded matrix, and outside of the band, it's not 0 entries, but they are exponentially small, exponentially in the distance away from the diagonal. So this situation I will also call sparse. It's almost sparse in the sense that they are not 0 entries, but they are exponentially small. And effectively, this is the same as having a sparse matrix for practical purpose. Well, in the calculation that I'm be talking about later on. So now these statements here, the existence of a basis in which H and O are sparse, or the corresponding statement here, are the motivation now for the following, which is the idea behind the calculation of equilibration times that I've used. I'm going to present to you, and I think it's a kind of cute idea to look at this problem, and it's the following. So what I do, motivated by what I showed you before, I everything, meaning the Schrödinger equation and the corresponding properties with respect in the eigenbasis of the observable O. It's an uncommon choice. You rarely write your problem in the observable eigenbasis, but this is what I'm going to do here. So these x are now the wave functions in the eigenbases OJ, and the HJK are the matrix elements of the Hamiltonian in the OJ in the observable eigenbases. And then I can write the Schrödinger equation in this simple form here. So these are now my wave function variables. I call them the x. The x is here, and the corresponding. Well, this is just like harmonic oscillators, sorry, oscillators if you want. And the integrated Schrödinger equation can looks like this. I use the integrated version because there's one thing one can maybe see more clearly, that in this equation now the diagonal elements of the Hamiltonian in that observable basis, they set the frequencies, the natural frequencies of the oscillators x, and the HJK are the couplings between the oscillators. So what I'm doing here now is, I'm talking about oscillators and couplings. I consider the Schrödinger equation, or the components of the Schrödinger equation, as classical oscillators that are coupled. And the plot I'm going to show you is, so the idea is now I study this problem here, the Schrödinger equation, as a network of classical oscillators in Hilbert space. And because of the reasons I gave before, it's going to be a sparse network. So there are not going to be too many links in this network. And now here's my illustration. So each dot here corresponds to one of these xj variables. What I've done now, I've ordered these variables. I mean, it's just a way of plotting them. And this axis here, according to which they are ordered, is, sorry, that's a bit small for you to see probably, is how much the corresponding eigenvector, the eigenvalue corresponding to this vector here, deviates from the equilibrium expectation value. So now here we are in the furthest non-equilibrium state. There's only one in my plot, and here at 0, these are all equilibrium states. And this is something that is physically, just a second, physically realistic, that equilibrium states are typical. There's many more equilibrium states than non-equilibrium states, and I've plotted them all here. And these are some states in between at other values of the observable eigenvalue and so on. And then I've drawn some lines which are the non-negligible couplings. Some of these oscillators in this sparse networks are coupled, and many are not. Leo,
yeah, I'm just wondering, just to be clear, I'm following you. When you say classical oscillators, do you mean like xj's are now in phase space because this is first-time derivative equation?
So xj is now, say, just a classical variable.
No, I know, but is it in phase space? Because the equations are first order in time, so that's what I'm wondering.
Yeah, so you're asking whether there's well, no, because if it would be second order, it would make sense to define a phase space, right?
Well, that's what I'm asking.
Yeah.
Schrödinger equation is first order in time, plus it has an I. So I don't understand, when you say classical harmonic oscillator, do you mean like figuratively or literally? Like
no, figuratively. So classical variables that follow this first order differential equation, that's it.
But maybe you can think of it as some phase space.
No.
X and P and something.
Nothing of that like that is meant here, yeah.
Okay, thank you.
Yeah. Yeah. And actually the whole slide here is going to be an analogy to motivate the type of result. It's not going to be the actual calculation, is not even using precisely this formulation, but I think it's instructive to look at it in this way. So the instructive point is now, if I want to study equilibration, and I say I start in a non-equilibrium value here, and the system is equilibrated when the state ends up in one of all these here, any or many of those, or one, doesn't matter. This will all give equilibrium measurements then I can consider this problem as like an excitation traveling through this network. And I can ask, well, how long does it take to go from here to here? And this brings me to a type of question that you have heard about here before also, that is Lieb-Robinson bounds. That is a mathematical statement that tells you, well, if I do something here at time 0, when can I expect when I can see an effect of that at some other site at some later time. This is a bit the spirit of Lieb-Robinson bounds, and in fact there is a classical analog of Lieb-Robinson bound that is not so well known, but it's really similar in terms of what you look at, and you can make a statement. These are all bounded variables, so they cannot be infinite. These are all phase variables essentially, and you can ask how long does it take me to go from here to here, and you can estimate this by using a classical Lieb-Robinson bound, and that is like the spirit of the calculation that I'm going to show you in the following, or I'm going to show you the result. 5 minutes, yeah, good. So equilibration through the network, and this is the result. I'm not going to tell you anything about the derivation. This object here, it's sometimes called something like a butterfly velocity, doing something at time 0 to the oscillator k. What is the effect that it has at time t on the oscillator j? And I look at the size of this effect, and then the result is that this, or the logarithm of this, is bounded by this quantity here. And the important ingredients in this here are, well, the norm of the Hamiltonian. Then this here is the distance in the usual Lieb-Robinson is like the space, the spatial distance. Here it's a distance in how far from well, how large is the one, or it's a distance in observable eigenvalues, if you want. But I'll illustrate this result with a plot, noting that this k here, in this parameter k, locality is encoded. I'll come to that in a second and in which way it is. This is a plot of this result here, and if you have seen plots of Lieb-Robinson bounds, well, you have all this morning, I think, then this is the similar type of plot. This is distance, and here it's not spatial distance on the lattice, but it's distance in this distance here, OK minus OJ, and this is time. And then the usual statement of these bounds is that if you if say the distance OK minus OJ is large, say 1, then it will take at least this time here to have a significant size of this property. And the interpretation is to have, say, if I start here in the oscillator, in one oscillator in non-equilibrium, this will be the interpretation of the whole thing. It takes that time to get from here strongest non-equilibrium value to equilibrium. It will take at least, or it will take at least this time here. So this is the type of result that can be now interpreted as equilibration. Why does it work? Because usually I could say, if I estimate the time to go from equilibrium to non-equilibrium, I would get the same bound. But the difference here is that typicality, the fact that I have so many equilibrium values, will bring me automatically to that side, and the bound will be a good bound, whereas in the other direction it will be a bad bound. So it's only useful for the process of equilibration, I think. Okay, this is the interpretation I just gave. And I will get a bound on how fast equilibrium can be reached. And this equilibration time is this time scale here, which in this bound gives this red horizon here. Okay, no words about the proof. I told you the bound depends on the locality parameter k. I still haven't told you what that is, but if you plot the bound for different values of k, this is k equals 0.1 and this is 1, then in the case where k is larger, the relevant time scale will be much shorter. So this here will correspond to a less local system, so long-range couplings, or even something less local. I'll tell you in a second. And this is a very local system. Think of a nearest neighbor system. So what is this locality parameter? It's a product kappa GR, and these are the quantities. Kappa is k body observables. So I can have, say, a magnetization. Sum of single spins is one body observable. correlations would be a two-body observable and so on. So then the magnitude of terms in the observable, this is the definition of the observable here, plays a role. And then I have the maximum local interaction strength. This is where the Hamiltonian comes in, and this quantity is the one that encodes properties of the Hamiltonian. At first sight, it just doesn't look like long range, short range. You can't see it here, but I'll tell you, you go from a long range to a short range system, and this G will change in a significant and interesting way. So let's show you some, well, I'll skip this one because I absolutely want to show you this one. Timescales and long range interactions. So now I look at a model, just, well, as Nicolas said, everybody does. It's the Ising model. It's the long range version here. And as an observable, I use the magnetization. And then what we did is you calculated the estimator of the equilibration times. It's plotted in red. And we did some numerical, some numerics. So this is the bound, the blue symbols are the bound I showed you before. The red are model calculations for this year. And this here is not the equilibration time, but it's divided by some factor. So what really happens, the bound is up here as it should. So it's a proper bound. But if I rescale the bound, I find that it nicely captures the functional dependence of the equilibration time on the locality parameter. And I think that this, I feel, tells me that this is the right parameter. Of course, the bound will overestimate the equilibration time, but it does so in a way that nicely captures the functional dependence. So I have the feeling that this property G is really the essence in some way, I hope, of what makes the long-range systems equilibrate, in this case, faster, or at least in the cases where this bound is a good bound. Okay, I must come to the end. Take-home message, I would say, in terms of concepts, local Hamiltonians and observables can be interpreted as a sparse network in Hilbert space, and I think it's a kind of interesting approach to this problem. In terms of methods, I would say estimating propagation in Hilbert space with classical Lieb-Robinson bounds is what I've used to come up with a result like this. And in terms of physics, the equilibration time depends on the locality of the Hamiltonian and the observable, so both. And these quantities, kappa, G, and R that I showed you, at least in this bound, seem to capture the effect in a quantitative way. Finally, as I said, not all physics is typical, or maybe most physics is atypical. What was one of the motivations that brought me to this kind of calculations. And then finally, open questions. I mean, I have this funny notion of locality with this G parameter that I showed you. It would be nice, of course, to really have the locality in the usual sense as we know it, like long-range exponents somewhere in this result, but I wouldn't know how to get there. And the question of how tight these bounds are. And then I think the really interesting thing to do, and I have no idea how it goes, what to calculate, not a bound, but the typical equilibration time taking locality into account. So something like random matrix, but including all the locality. That would be an awesome thing to do, but certainly a hard problem. Finally, that's the paper on which all of this is based, and thank you for your attention.
Questions?
So I have a question about the role of the initial state there, right? So I would think that if you prepare experimentally some state, the pure state, like for ideal pure state, it will be a superposition of exponentially many eigenstate of whatever local operator you in general have, right? So you start with something that is exponential, number of states in your basis. Yeah. And it's true, it's sparse, but you start exponential. So yeah, can you comment on that picture versus that picture that you have in there? And the role also of the initial state and how many of the eigenstate of the observable are.
Yeah, so I think you were referring to this picture here. I mean, as a illustration at least. So if I don't start here in that space, in that state, but in a superposition of a substantial of exponentially many, yeah. So if the state is if it's a non-equilibrium state, and only then it makes an interesting problem, then I would say that it would still, in this very simple sketch, it would correspond to still using only this part here, because it will always be, as you know, that the vast majority of states is here in equilibrium. So even if I take exponentially many states that are in non-equilibrium, then they will be only a tiny portion. So I think if I don't use only that state, but this here will in a large system already be exponentially many states, well, on the scale of the simple sketch. So, and then I would say, okay, if it's not only this state but here, then I would just use as a simple estimator the distance from this here to that. Or if you say, well, but maybe I have a tiny occupation of this state here as well, and maybe even of that one, then at some point you would need to write something. Well, you would need to give a number. How much do you want to see? Or let's put it like this: for how much non-equilibrium you allow in your final observation. No, this wasn't well explained. I'm sorry, but I believe
maybe I can comment. So I mean, you've chosen a specific basis, which is this observable, right? The eigenstate of the observable. And what I'm like, the picture I have in mind, you start with exponentially many, you end up with exponentially many.
Yeah.
Right. So
absolutely.
Right, yeah.
But I would say the exponentially many, if it's a non-equilibrium state, will be somewhere in some region, and in the end they may be all spread out here. So it's not about going from here to here, but the time going from here to here has the same bound as going from here to here and from here to here to all the other states. So the bound will be the same. So this is why going from here to one state and going from here to a superposition of many of these states has the same bound. And the same is true if your initial state is many, but you say they are not in equilibrium, they're only here, then the bound going from here to here will be the same as going from all here to all of here.
Yeah, I think it's a related question, because if I think of a local operator, I imagine that it has at most d eigenvalues, massively degenerate, right? And so your eigenstate are at most divided in d or a finite set of eigenvalue. They don't enter this discussion, right? The eigenvalues don't enter, right? Or they do?
Sorry, the eigenvalues
of the operator. So I mean, a local operator is by definition exponential large degeneracy.
Yeah, no, the degeneracies do not enter, and the eigenvalues enter in the bound of, I mean, in the bound here, these are the eigenvalues. But for the calculation degeneracies here, different from the typicality results you might think of, they don't enter here.
Sorry, very interesting talk. Just a related question, I think, to the first question. You invoked the idea of like how this is like banded matrices, basically, because in the eigenbasis, the O is the eigenbasis of H is a banded matrix.
Yeah.
So are you thinking of locality in space, or you're thinking of locality that the wave functions have finite support in Hilbert space? Which one is it? Because a local observable, like spatially local, can still have a support of wave functions which is extensive in system size.
I'm not sure on this. So locality of the observable is whether it's
is it in actual like space of many body system, or is it actually in the eigenbasis of
no, it's not in the eigenbase. It's in real space that you say. So for example, the magnetization, like a sum over all spin sigma z components, is a sum of one body observable, and this in this sense it would be a local observable. This is as local as it can be.
But it doesn't need to have a finite support in the eigenbasis of whatever Hamiltonian you may have. That's not guaranteed.
No, the eigenbasis really doesn't play a role for the notion of locality here.
Okay.
Yeah.
I was wondering, does your setup, can it be, in a sense, improved to also take into account symmetries of the Hamiltonian? For example, if you have a conserved quantity and your operator couples to this conserved quantity where the late time dynamics would be dominated by some hydrodynamic decay, so some very long time scales, do you think it's possible to kind of incorporate these symmetries and make predictions about the time scales of this hydrodynamic behavior if you have this conserved quantity?
So I haven't thought about this. This is I think my first direction to think about this would be, well, can't I make this argument in any of the symmetries, in all of the symmetry subspaces, and combine it in some way, because it should go through in just the same way within that subspace if I have a symmetry, right? So could I do this and then have to combine the bounds in some way to reassemble the whole result if I have an initial state that extends over different subspaces or components of the symmetry? But this is just a rough guess now.
Thank you for the nice talk. I may have missed this, but when you were discussing that result about these almost banded and almost sparse matrices with the exponentially decaying elements, is it known precisely how much you can treat those as banded or sparse? Like if you just take all the exponentially decaying elements to zero and to still get the same eigenvalues? Is that stated in the paper? Or?
So there's a clear statement, again in forms of a bound, but that the elements outside of the band are upper bounded, or their modulus is upper bounded by, and then there is a precise exponential that is given in terms of some properties of these matrices. So you have the exponential form of the decay, or you have a bound on the exponential form of the decaying size of the matrix elements. Is that what you are asking?
And the result is that if you have this form, what do you get in the eigenvalue spectrum? Or you get some, what is the utility there? Can you treat those as a truly banded matrix, or?
Well, this I would say must depend on the problem you're studying. I mean, if you set up a physics problem that really probes that one small far off the diagonal element, I think you can set up a physics problem that has this element kind of as an outcome, or where this element dictates. If you say you do something and then you measure precisely this eigenvalue of this and that of the observable, or something, I think you have a chance of probing that. So I don't think you can make a general statement, these small elements will never play a role. But if you do something that is of a very collective nature and you don't single out certain states by your physics setup, then I think you'll find situations where you can neglect them. And in the result we actually that I actually show in this bound here, there is, I mean, we don't assume at some point that this almost banded matrix is banded or something. We treat all the elements and bound them in some way, but this is so we don't cheat in the way of declaring the matrix as banded. But it helps to know that this is all small, and to have a bound on the size of these elements.
Mm-hmm. All right. Thank you.
Just a basic question. What's the connection between this result and your definition of equilibration?
The definition of equilibration so for me it was the motivation to look at this problem in this way here, because the definition of equilibration that I used was the one with the equilibrium subspace. So you look at a subspace of Hilbert space spanned by the eigenvectors of the observable with eigenvalues that are equilibrium or almost equilibrium. So these states here on that line, this is the equilibrium subspace as used in the definition of equilibration that I had. And now this definition tells you, you call your system equilibrated when most of the weight of the wave function is in that space. And this is why I think this notion of this definition of equilibration gives me a reason for the interpretation. Well, I have to travel from here into these states. I have to be in those states to be equilibrated. And this is why I think it's useful in this case. If you only look at equilibration value, at equilibration at the level of expectation values, you may have a superposition of those states or of those states that give you the equilibrium value of the expectation value, and then it's not very helpful.
Okay, thank you.
You don't look. Yeah, I can try to explain again later. Yeah.
Okay, so let's thank Michaela again. And
thank you.